Hello, everyone. We'll get started shortly. I hope everyone's doing well. We are doing the space after, I think, maybe like 4 weeks now, 3 or 4 weeks. I was busy traveling. I was at ICML and other travels, so we were unable to host the paper space for these past few weeks. But yeah, we're getting back to it, and should be exciting. I think we'll also be covering a few of the. We'll of course be covering some papers from the past week, but also a few papers from previous weeks as well. So yeah. Aaron, you want to add anything?
Oh yeah, so I just moved to San Francisco and I'm organizing a meetup at Dollars Park with Lucid Blend. So if you guys are interested, please join us. Oh yeah, also the AI scientist, the presentation is going to be a bit late. It's going to be from in 20 minutes. So instead, the second paper is going to be the first paper for us.
Yeah, so I guess, yeah, we'll get started. Is Charlie in the space? I don't see him here.
I can ping him.
So yeah, the first paper, so I've pinned it's not coming up. Oh yeah, there we go. So the list of papers is pinned to the top of the space. So we're actually going to start with the second paper instead of the first one because the authors aren't here yet. And so we're just waiting right now for Charlie to join the space, and he can then talk about his paper.
Oh yeah, okay. Charlie is already in the room, so can you find him?
Let's see, where is he?
Maybe he can request.
Yes, if you request, that'd be easiest.
Okay, he just did request.
Hmm. That is weird. I don't see anything. Are you able to see him in the room? I actually did not see him in the room at all.
Yeah.
Okay, I don't know what's going on, but we cannot, why he's not in the, it's like, it's not showing up that he's in the room, in the space in the first place, I think.
Yeah.
That is really weird. Okay, let's see here. Does anyone else see him in the room, or is it just some sort of issue on our end? Maybe Charlie, if he's in the space, he should leave and rejoin.
Oh, okay. So he said he tried to sort of react, but he couldn't.
Is he joining from his laptop or his phone? Like sometimes if you're joining from, yeah, maybe. one device, you should try a different device. Because remember, like I think in the past, Aaron, you tried joining before, and one time it wasn't working. You had to join from a different device.
Yeah, actually, he just said it worked. So looks like there was some advantage.
Oh, well, okay. I do see him now as in the space, so I can invite him to speak. Okay, he should be a speaker now.
Awesome.
Oh, hello.
Nice.
Okay, good. Were you joining from like a different device and it was not working from there or something like that?
I was on my laptop and then I just left and rejoined and it worked the second time.
Okay.
So.
Okay, cool. Perfect. Yeah, thanks for joining us. And yeah, we'd love to hear about your paper. Yeah, so feel free to start.
Yeah, so I'll begin. So so this is a paper I just put out with some collaborators from Google called Scaling LLM Test-Time Compute Can Be More Effective Than Scaling Model Parameters. Basically, what we're interested in is on sort of challenging input questions that we might ask a language model. Can we enable the language model to use additional test time computation to improve the accuracy of their responses? So this sort of has two potential implications, or two big ones that I'm interested in. One is the potential for using smaller models plus test time compute to perform better or on par with much larger models that can only fit on like a data center GPU. And then the second interesting use case for something like this is for essentially generating synthetic data. So if you have a process where the model can sort of improve its own outputs at test time, then you can sort of use those outputs to then train the model and sort of improve itself in a little bit of an AlphaGo style way. So we explore how can we most effectively scale test time compute. And we look at sort of two mechanisms by which this can be done. One is by searching against a verifier, which predicts a score at the end of each step. I guess I should specify that we're focused on math problems in this setting because these are sort of very challenging reasoning problems for LMs, though we expect many of our techniques should apply in other similar reasoning settings. So we do search against a verifier, a process-based verifier, which looks at each individual step. And then the other mechanism by which we scale test time compute is with revisions. So having the model propose an answer, look at its previous answer, and then propose a new improved answer, and doing this iteratively. And we want to know how to most effectively scale test time compute. So for each of these mechanisms, there's sort of different decisions you can make. There's some different hyperparameters. So with search, we could do sort of best of n, which is a very naive approach where you sample n complete solutions and then pick the best under a verifier. Or we could do like a tree search against the intermediate steps. And we can also vary like the beam width and all these different parameters with respect to the search. Similarly, with the case of revisions, we could sample long chains of revisions, or we could sample like shorter chains of revisions, but have multiple of them in parallel. So we actually find that depending on the question difficulty, different decisions with respect to scaling with respect to scaling test time compute perform better. So in the case of search, on easier questions, it's often the case that best of n performs the best or like on par with like more sophisticated search techniques. Whereas on harder questions, doing like tree search is much more preferable to doing best of n. Similarly, in the case of revisions, we find that there's sort of an optimal ratio of an ideal ratio of sequential revisions to parallel revision rollouts, depending on the question difficulty. So in easier questions, it's slightly more preferable to use like longer revision chains, whereas on harder questions, you need to find there's sort of an ideal balance point. So using this insight, basically what we do is we set up we define what we call compute optimal scaling, where we select the best set of hyperparameters depending on the question difficulty. And once we do this, in the case of the PRM search, we're able to improve test time compute scaling by, in some cases, like a factor of 4. So we can reach the same performance with 4x less compute that we would normally get with like a more naive scaling strategy. And we find a similar thing in the case of revisions, also about a 4x efficiency improvement by optimally allocating compute. And then at the end of the paper, we put this all together to see, okay, so now we figured out sort of the different dimensions by which we can scale test time compute and how to most effectively allocate test time compute. Now that we've done this, how can we actually outperform models that are trained with larger parameters? So we want to compare like a model trained with m times more parameters. In our case, we look at a much larger model trained with 14 times more parameters. If we use instead a small model, but apply additional test time compute, can it be more effective? And we find that, again, sort of the answer depends on question difficulty. So, and there's also some assumption you have to make about how much inference compute you're expecting to do in your setting. So in a production setting, you might have a very large inference budget, whereas if you're not shipping your model into like a production endpoint, maybe it's much lower. So what we find is on easier questions or in settings where you have sort of a lower inference load, test time compute can outperform scaling parameters. However, on much harder questions or in settings where you have like a very large inference compute expectation, then scaling parameters is often more effective. Yeah, so I'd say those are the main conclusions. I'm happy to take any questions.
Yeah, if people have any questions, they can reply to the space with a tweet, and we can put up any questions. Aaron, did you have anything you wanted to add, or any questions?
Oh, can I ask? Okay.
Yeah.
Thank you. So there's a similar paper released recently, slightly similar, I guess. Large language monkeys scaling inference compute with repeated sampling. What are differences between your paper and their paper? Did you read the paper?
Yeah, I've read their paper. Yeah, so I think there's a number of differences. I think their paper is mostly concerned with this question of this. So they mostly focus on the setting where you have like an Oracle verifier, which is like if I can look at the ground truth correctness of my answer, or run the code against some test cases and determine like somewhat objectively if it's correct or not. And so in this setting, if you scale just like best event or whatever, you can get like with 1,000 samples or whatever in math, you can get to like 95%. However, if you use instead a learned verifier, which is in reality probably the more practical thing in a real production setting, you're likely not going to have a ground truth verifier that you can check against. So if you instead use a learned verifier, you can only get like half of that. You can get up to like 45% instead of 90% by scaling test time compute. And this is just because the model makes errors. So their paper was sort of focused on the Oracle setting, and then they point out that there is this gap between a learned verifier and a ground truth. Our paper is more focused on, in the learned verifier setting, how can we most effectively scale test time compute? We don't concern ourselves too much with like the Oracle setting. I would say that's sort of the difference between the two papers.
That makes sense. Thanks for your answer. It's interesting that there are two papers coming from the same group. Google, with very similar ideas. Obviously, I personally think yours is more sort of sophisticated.
There's actually a third one that came out. I didn't even notice it until after it came out, like a few days before ours as well. It's called an empirical analysis of compute optimal inference for problem solving with language models. So also tell people to check that one out. It's relatively similar to our paper. It does some different things, but yeah.
So yeah, I'm very bullish on tree search and verifier. There was actually another project by Multi-On about Agent Q, where they showed like MCTS and verifiers effectiveness on agent. So yeah, I'm very excited.
Yeah, I think there's a lot of potential here. I'm particularly excited about like the angle of using test time compute to generate data that can then be used for training. At some point, you run out of tokens on the internet, so you need to be able to generate tokens. I think that's very exciting.
Yeah, absolutely. Oh, by the way, there's a question by Ben Schultz. So what is the criteria to consider for what exactly are the harder questions?
Oh, how do we define difficulty? Yeah, that's a good question. So in the paper, we do two different things, but we define difficulty relative to the base model itself. So how much does the base model struggle with a given question? So the first version of difficulty we consider is oracle difficulty, which is simply I sample 2,000 outputs from the base model on each question and look at how many of them does it get correct, and then we create sort of 5 difficulty bins. So the questions that it gets right 90% of the time are the easy ones, and the ones that only gets right 5% of the time are the hard ones. This, of course, uses oracle information, so you have to know the ground truth to know this difficulty, which is why we call it the oracle bin. The oracle difficulty, and then there's also the predicted difficulty, which instead of using the ground truth correctness, we use a verifier's prediction to bin the difficulties. I guess both of these are like pretty naive. You could do like more sophisticated things to predict the difficulty, like fine tune a model to directly predict it, which would be much cheaper. Directly predict it given the question, but yeah, that's how we define difficulty in the paper.
Makes sense. Any other question? Anish, do you have any question?
No, I think Aaron, you kind of like were also asking kind of similar things that I was thinking of. So yeah, I think I mean it's just very exciting work, and it's interesting to see how much of the pre-training budget can be shifted to the inference budget. I think this is a very interesting avenue of I guess trying to gain some extra performance from these models. I guess one thing is like, certainly like this is interesting for math and I guess also code, where I think you make this point of like learn verifier versus like an Oracle ground truth verifier.
Yeah.
Where I think in math and code, obviously those are much easier to probably have these sorts of ground truth oracles and ground truth verifiers. But then in other domains, like I guess that's my biggest question is like in outside of math and code, how can this be applied? And I think the answer to that is probably that you need to have some sort of learned verifier, some sort of learned critique model or something like this, basically. But I'm curious if you could maybe speak to that a bit, like how these sorts of approaches would be applied outside of the math and code domains.
Yeah, for sure. So in our setting, we are focusing on learned verifiers, and it's a little bit easy to generate the verifier data because we have a training set where we know the ground truth, and we can just like generate answers and then fine tune a verifier on it. I imagine though that like you can fine tune a verifier for many domains. You would just need, I mean, you might need to hire a bunch of humans to like help you collect some labels, but you could imagine, like similar to how you can instruction tune a model to do many different tasks, you could do something similar to get a verifier that can verify many different tasks if you collect a decent amount of data. It doesn't require a ton of data. It's on the same scale as like normal fine-tuning data sets. Let's see, what else? Oh, I guess the other thing that's interesting to note is I think early on there was a lot of papers sort of prompting models to do like critique and revision. And this works well on like fairly easy tasks like summarization, harmlessness, like things that don't require like really complex reasoning. However, once you apply these ideas where you're just like few shot prompting a model to do revisions or critiques to harder tasks like math or code, it doesn't work very well. Or like it fails to beat simple baselines like majority. So in these settings, we actually have to fine tune verifiers. However, it is possible that like as models get better and like the pre-training data is like further refined towards capabilities that we care about, it's very possible that like many models will be like effective critiquers or verifiers on much harder tasks kind of out of the box. But with today's models, we have to fine tune them.
Yeah, forgot to mention, but this Agent Q model uses self-critique. So yeah, it's
Yeah.
very relevant, I guess.
Yeah, I think it's easier to critique on. It might be easier to critique on some like agent tasks because like it's kind of like if your task is say like buy me this item, it's pretty easy to check if you did it correctly. You can just look at like the Amazon receipt email. It doesn't require complex reasoning to do the verification in that case.
Yeah, it's kind of
Yeah.
crazy that we are almost solving IMO questions before solving web navigation.
It is kind of interesting. Yeah, I think it's harder to. I think the answer is that it's like harder to get the data for web navigation. Yeah.
Okay.
Cool.
Any other question?
Yeah, I don't have any other questions, and I don't think there's any other tweets in the space about it. But yeah, I think this was really, really interesting. Thank you, Charlie, for presenting this paper. And I think the surrounding discussion about it too was very interesting too. So yeah, thanks for joining us, Charlie.
Yeah, thanks for having me.
Okay, so
cool.
Actually, Cong, the first the AI scientist paper author is now on Space. Can you find him?
Okay, let's see here. I don't see him. I guess I don't know if we're having the same problem as before. Can he request to speak? Let's see here. So yeah, we're trying to have. So we covered the paper by Charlie, which is actually the second paper on our list, and now the first paper on our list. The author of that paper is going to talk about his work, but now I need to have him join the space and request to speak.
He already requested.
Yeah, again, I think it's a similar issue of maybe he can try to leave and rejoin, but I think we're having a similar issue that he's not showing up.
Yeah, it's crazy that we cannot even let people speak, even though we can solve IMO questions now.
Yeah, I guess yeah. Look, XAI is doing great things, but they also need to work on the X team needs to work on the spaces more, I think. Let's see, did he?
Okay, he rejoined and requested.
Yeah, I don't see him. Do you see him at all in the space?
No.
Yeah. Or like, is he joining from his laptop or his phone? Like, if he tries joining from a different device, I don't know.
Okay, let me ask him.
Yeah. Sorry, everyone, about these technical difficulties. It's always the problem with these spaces.
Okay, so he's using laptop.
Okay. Maybe he can try to use his phone if possible.
Yeah, so he showed me his screenshot, and he's definitely in the space.
Yeah, I think it's just a problem with I think also the desktop or web also has a lot of issues. So, yeah, ask him to try on the phone if possible.
Yeah.
So yeah, the next paper, like this author is going to talk about the AI scientist paper from Sakana AI. So that should be quite interesting.
Can you make me co-host? Maybe I can help.
Yes, I have sent you a request to be co-host.
Okay, he's on his phone and requested.
Yeah, I don't know. It doesn't seem to be working. Do you want to move on and we can try again later or something? I don't know.
Yeah, that works too. Okay, okay, I can probably give a talk on my next paper. Then meanwhile, you guys can sort of resolve that problem.
Yeah, I'll wait. Yeah, I'll DM him and see.
Yeah, sounds good. Okay, so yeah, let me talk about Gemma 2 and PaliGemma. These are each of these kind of short papers in terms of like contents, because they are like extensions of like existing models. So, well, I'm sure you guys already know well about these papers, which were released a month ago. So let me start with Gemma 2. So obviously this is the successor to Gemma 1.5. So yeah, it's more or less minor update, but the performance improvement is quite significant and uh, achieves state-of-the-art performance on their respective scale. So they released from 2 billion to 27 billion models, and 27 billion models were trained on 13 trillion tokens. So for training, they used distillation. Knowledge distillation led to significant improvement in training compute efficiency over the baseline. And they observed significant improvements in terms of score on their benchmark, which was like from 60 to 67 points when they distilled their 2B model from 7B. So this advantage of distillation actually persists across different model sizes. So this is a very promising method. And their post-training procedure is very standard. They used SFT and RLHF. Architecture-wise, they also used GQA, and they also used local attention with full attention interleaved for better efficiency. And they used logit soft capping, which makes the logits of each attention layer stay within the certain interval for stability. Um, my question is, why is the ratio of feed forward dimension to D model so large? So like it's typically set to around 4, right? But Gemma 2 27B has like 16 times. So they have like 16 times larger feed forward dimension than D model. If anyone knows why, let me know. That sounds very big. And Google model tends to use this very large feed forward dimension for some reason. Obviously, it's very efficient in terms of TPUs, but I feel like it's kind of wasteful. If you're using MOE, MOE sort of behaves as like a large feed forward dimension, but MOE is doing conditional computation, so it's efficient. But in this case, their model is dense, so it doesn't make sense to me. Yeah. So that's for Gemma 2. So yeah, actually there's not much to talk about Gemma 2. Anyway, for PaliGemma, basically it's an open vision language model that is based on the SIGLIP SO 400 million vision encoder and the Gemma 2B language model. So it achieves strong performance on a wide variety of open world tasks. Architecture-wise, it consists of SIGLIP image encoder with linear layer projection after that. And its output features, along with the corresponding text, fed to the Gemma Gemma decoder for textual output. Each component is initialized from publicly available checkpoints, and it uses prefix language model masking on the decoder side, meaning no masking on attention across image tokens and text input tokens. So I think, yeah, this sounds kind of interesting because they are using decoder model, but they are doing prefix LLM masking. So in terms of training phase, stage 0 is just unimodal pre-training. So they trained Gemma and SIGLIP separately. Well, they obviously are using publicly available checkpoints, so they didn't really do it in this paper. So, and stage 1, they are multimodal pre-training. So it's a long pre-training on a carefully chosen mixture of multimodal tasks. And notably, nothing is frozen in this phase. And stage 2, they increased resolution, continued pre-training at higher resolution. And at the end, they did transfer. So turned the base model into a task-specific specialist. So they performed a bunch of ablations, which was very insightful. I really love ablations. So they found that freezing is typically worse than unfreezing, especially worse when the language model is frozen. Unfreezing the image encoder leads to significant improvements on tasks requiring spatial understanding. So this was kind of interesting. So the thing is, there have been many ablation results from many vision language model papers for the last 4 years about freezing versus unfreezing with different contradictory results, even among the same institution like Google. So I'd like to know what led to this lack of consensus, and if we should believe this, their claim is sort of like the final consensus. Yeah. What do you guys think?
Yeah, does anyone have any questions about Gemma and PaliGemma? Maybe people want to reply with a comment or anything, feel free to do so. One thing interesting, kind of like a separate like paper or something about Gemma. Like they also did like the sparse autoencoder training of Gemma, which is quite nice. That they trained those SAE models and released it openly. So that's also worth checking out if you're interested in interpretability research. Yeah, they did that for I think the 2 billion and 9 billion models, where they did it for all of the layers, and then I think the 27 billion model they did it for a select number of layers. And so yeah, someone was saying, oh, someone should build a Golden Gate Gemma. So maybe that could be a fun project for someone to do with the Gemma models and the Gemma SAEs. It's called Gemma Scope. Yeah, that was the only other thing I kind of wanted to add here.
Yeah, so I'm reading a comment, and David says a larger hidden dimension could just be about more expressiveness and storage capacity. Yeah, I think so. But I wonder if that's better than larger D model. That, from my experience, that typically leads to better performance for given compute budget. Anyway, so Cong is now joined as speaker. Thanks, Tanish.
Yeah, just so everyone knows, our list has been a little bit kind of out of order because of all the difficulties. So we went the scaling LLM test time compute. We did that first with Charlie. Then we covered Gemma 2 and PaliGemma that Aaron just covered, and now we're going to cover the first paper, AI Scientist, which the first author Cong will present that right now. So just for everyone to know what the order is, because it was a bit out of order. So sorry about that. But yeah, Kong, I guess you can take it away.
Yeah, awesome. Thank you. Can you hear me?
Yes.
Yep.
All right, nice. Nothing like a few technical difficulties to start the presentation. Um, yeah, thank you for laugh reacting. Yeah, so thank you so much for having me, and I'm super excited to talk about the AI scientist. And we're incredibly excited by the reception from the community so far. And yeah, I wanted to shout out my co-authors as well, Chris and Rob, as well as Jacob, Jeff, and David, who've been awesome collaborators on this work. And let me just dive right into the details, I guess. So the focus of our work is envisioning whether or not current frontier LLMs can entirely take over the scientific process. So this stretches from idea generation, from implementing experiments, iterating on them, visualizing intermediate results, writing the paper, all the way to reviewing, all powered by recent advances in frontier LLMs. And moreover, this kind of process that we create in the AI Scientist is iterative and open-ended. So already what we have is the language model can start out with a few ideas, try them out, see what works, and based on that, can refine and select the next best proposal from the list based on that. And we're already like blown away by what the AI scientist can already do. Like we've been impressed by the creativity of its ideas, the fact that through our process, the model is able to sort of communicate its insights in a sort of human readable format has been really useful for us to sort of debug and get inspired, I guess, by what's been output. And all of our code, I guess, is open source, and we truly believe that this is sort of, this is like the Will Smith eating spaghetti moment of AI science. This is the worst it will ever be. And right now, the paper qualities is sort of, basic kind of ideas building on established frameworks, maybe one or two steps above the baseline. But we really envision sort of like whole AI communities forming out of this in the future. So more advanced paper generation, more deep ideas, um, with the vast amount of progress that's coming in foundation models, we're, I guess, like slightly taken aback by what we can currently achieve, but we think that next generation of models, we could even just be blown away by the quality of ideas and experiments that come out of this system. Um, and I guess yeah, one other thing like that I kind of want to discuss is that we're sort of just we were surprised at what current systems could already achieve, and it was super um, straightforward to sort of for us to sort of like bootstrap from earlier prototypes of the AI scientists. So early on, we had I think Chris shared quite a few photos of our earlier mock-up of AI scientists, where it's literally just one or two experiments, write up the idea in Markdown, display it to us. It's like 4 pages long, but we just kept adding it. We just kept asking the model to do more stuff. So like go deeper on the ideas, revisit, prior experiments, keep like a logbook of progress, even up to, writing a full paper in LaTeX format, which we thought was like impossible for current models to do, together with pulling sites from the internet. And I guess for us we see lots of future improvements. So, the standard prompt engineering, perhaps like fine-tuning models to be able to do this. But I guess we are also interested in kind of starting a conversation around what should the role of AI be in future science. Can we have these models at a point where we can trust the science, where we can build on it? Can these papers even be, submitted to iClear as just a regular paper? Can we even like produce stuff that's good enough to be presented as a full paper at a science conference? And at that point, we don't even know like who's going to stand in front of the poster and present it. So yeah, lots of future work, and we've been super excited by just the reception so far. Lots of people commenting on the GitHub, and yeah, we're really excited to see what the community thinks about this. And one thing I do really want to like stress is we really do believe that this is the worst it will ever be, and we cannot wait for what it's going to be like with a few future. What is V2? What is V3 going to be? This is really the hand with seven fingers version of AI papers. So yeah, happy to take any questions about it.
Awesome. So are you sort of envisioning this AI scientist project as sort of like a community-driven project, like Open Devin and Sweet Agent?
We definitely welcome it. Like all of our code is online right now, and just today we accepted maybe like 3 pull requests. I think people are really excited to build in it, so integrating more models into it. I think people have been suggesting different ways of getting the idea generation process going. So right now it's really just bootstrapped off of the LLM's own thoughts, but I think we have a pull request right now, which is even, can we take in existing literature, like a literature review, and based off of that, come up with pressing questions to answer about a code base. So yeah, I would definitely love to see community involvement.
Awesome. So another thing is, typically difficult questions like IMO questions, let's say, it's like and they do use MCTS and that kind of stuff. Have you tried something like that?
So I guess yeah, there's many places we could see that in the AI scientist pipeline. So maybe if I just hone in on, for example, like coding, for example. Right now it's basically just a sort of chain of thought self-reflection loop, and it gets, say, n runs, and each run you get like n shots at perfecting the code. But this maybe works for the kind of 100-line modification to existing code base. But if it had to do more complex ideas, I think definitely like more advanced search could be a great thing. Even with idea generation, paper write-up, like the actual technology that we're using in LLMs, we use Aider, which has a lot of bells and whistles. But for a large part of that, there is a lot of like reflection and good Python linting. But it could definitely be so much more advanced for sure.
Thanks for your answer. Kanish, do you have any question?
Yeah, there's actually one question in the comment, which is the AI scientist multimodal? Like, can it draw figures, etc.? So yeah, curious. I assume, of course, like you have all these figures, sort of like data and stuff, but maybe also there's like potential for the model to create like other sorts of figures, like explanatory figures and things like this. So yeah, maybe you could touch a little bit about how it makes all these figures and its multimodal capabilities.
Yeah, for sure. So right now we don't use any multimodal capabilities, and all figures are generated by a code. So we get visualizations just out of matplotlib and Python libraries, and these all get inserted into the paper via LaTeX. But absolutely, like this process has a lot of flaws. For example, if you were like just blind making a figure for a paper and just put it in with some LaTeX code, almost certainly, it's not going to fit the screen. It's going to, not even just be V-spaced properly. And I think future versions of AI scientists are definitely gonna need like multimodal capabilities, either for critiquing the paper, for generating new figures. For example, one of the main roadblocks, maybe even for submitting AI generated papers to iClear, is that a lot of papers rely on, strong visualizations to convey their point. You could obviously do some stuff in like LaTeX ticks, but that kind of stuff also needs a little bit of iteration. But I think this is quite a doable one. All we got to do is, upload the pictures of the PDF into, Sonnet, Gemini, OpenAI's vision capabilities, and we can easily get critique from that. The other thing it would be good for as well is for the reviewer. So our reviewer right now is remarkably good for only being able to see the text. So you might imagine that's just because, all figures are probably described in the text and all the main conclusions are still there. It can see tables, but it can't see figures. Even for the reviewer, I think we envisioned that if it could get all these pictures also in context, we might even be able to improve the performance like vastly superhuman, beyond already like sort of matching human performance right now.
Awesome. So another question from Ben Schutz. Has there been an effort replicating established papers that are on GitHub or Hugging Face?
Sorry, what was the question? I see the question. Has there been an effort to replicate established papers, GitHub, Hugging Face? Yeah, so that's a really good question, and I think that would be an excellent application of this kind of technology. So, as it currently stands, I guess the idea generation of our paper is very much, open-ended, driven by the language model's own imagination. But it could definitely just take, previous ideas, like other people's ideas, and just try and implement them. So one roadblock right now to this is that the AI scientist is really trying to make modifications on an established code base. So, for example, the AI scientist right now just tries to make diffs based on existing diffusion code bases, existing transformer code bases. But if you wanted to replicate, then you might need to, pull code from the internet. You might need to write code from scratch and test things. We envision this is definitely all very possible, but we'll need one more step from the current version. And a lot of the design choices around AI scientists right now is based on speed and efficiency. So all of our experiments, will maybe only take a few minutes. Training Nano GPT only takes, 3-4 minutes on good GPUs. And if we wanted to, replicate any kind of paper, we might need to expand quite a lot more compute and parallelize quite a lot heavier. So any like heavyweight experiment, we're probably going to need to run the AI scientist for days on that for it to get sensible results. But not fundamental limitations, but more just room for further improvement.
Yeah, I actually have 2 more questions. So yeah, this paper is so interesting that I can come up with many questions. So
thank you.
Yeah, one question is more like a suggestion or like something idea. So I think we could be more ambitious like this paper, and try AI for like say entrepreneur or something. Obviously, and that sounds very ambitious. So doing everything like writing pitch and everything. Obviously, each component was already sort of done by GPT-4, but as a whole. So yeah, if somebody releases something like that, I'd say, it's gonna be so hard.
Yeah, I think we've just been like super impressed like how well the AI scientists can just generate ideas for anything. So this also like connects to a lot of work in, I guess, like the open-endedness, like evolution through large language model communities. And essentially, by just iterating ideas, you can generate like new ideas for anything. So, new like RL agents, new RL environments, in our case, like new paper ideas. For like the entrepreneur case, like new business proposals, I'm sure like you could execute out of this. What we'd really love to see, like in the far future, is, like AI for like any kind of scientific discovery. Like, could we just hook it up? Could we propose ideas to like some kind of automated system, and just like see it evolve? Right now, I think a lot of these models are very specialized to code and are really good at that. So right now we've been looking at a lot of like code applications for the AI scientist, and also yeah for other like works in evolution through large language models. Most of these things are like evolved through code. Um, but yeah, even today, I think actually on our GitHub, someone was like, "Have you considered applying this to biology, or like physics, or yeah, anything?" Um, yeah.
I have a quick question. Of course, yeah, maybe it's probably answered in the paper somewhere, but just to like, if you could quickly answer, like, have you compared between all the models, which models like
hmm
seem to propose like maybe the most creative ideas? Like, yeah, have you evaluated like how creative some of these models, or how diverse some of these ideas coming from these models are? Like, which models are providing the most creative and diverse ideas?
Yeah, so we evaluate four models in our paper. So that's Sonnet 3.5, GPT-4, and then also we wanted to see how good, open weight models were. So DeepSeek and Llama as well. So Sonnet consistently, I guess there's, yeah, many components to this, but we find that Sonnet consistently proposes the best ideas, executes them with the most amount of skill, and can also do some of the out of the box thinking to get out of, previous failures in experiments. Also writes LaTeX code really, really well. Um, a lot of the weaker models tend to struggle quite a lot. So the success rate of Sonnet even is maybe only like 70%. You move down to GPT-4 and it's maybe about 50% success rate. But DeepSeek is by far the best option we find for open source. And in terms of creativity, I guess, a lot of the showcases that are in the paper are all generated by Sonnet. And I was definitely super impressed already by what we saw out of Sonnet on diffusion and Sonnet on grokking. Like it does cover like many bases and proposes some like wacky ideas for like 2D diffusion, like um, I think super fun one I thought was like a grid over 2D space that like scales the noise scheduler for diffusion, depending on like where in the space you are. And this is just not something that I would like remotely come up with. I'd probably just I don't know, look through the literature and apply what's already been done before. But this is yeah, it's funky. It's funky, and we learn a lot by watching it think.
So
And like, have you like also like, I don't know, like, because some models may be more creative versus other models are better at executing and things like this. So like, are you doing this all with one model, or have you also mixed around different models for different aspects of the task?
Yeah. So I think Sonnet is probably just the best all-rounder. So a lot of the um, success of AI science is really rooted around coding ability. Um, and for example, we use Aider, and Aider with Sonnet is just leagues above other models. Um, I think there is quite a lot of room for bringing in open weight models like DeepSeek, um, when there's less need for like strong capabilities. So, for example, DeepSeek's maybe like 20 times cheaper than Sonnet. So we could just really just focus on Sonnet for the code writing, or just unleash DeepSeek and let it do way more iterations on the LaTeX write-up, for example, and like fix all the small like LaTeX compilation issues. So I think a mix and match strategy would definitely be very cost effective, but I think I would definitely still go for Sonnet as just the all-rounder best.
Awesome. Yeah, Aaron, did you have any other questions?
Yeah, I wanted to talk about a little bit about like implications to like a real world. So well, some of us think that AI researchers, capability researchers are going to be like some of them are going to be replaced by say 2030 or something. So if you are currently a researcher, your job may be in danger by then. I mean, if you have tenure, you probably cannot get fired. But if you're in industry, let's say, what do you think, Kong?
I think only time will tell. I think it's super hard to predict what future capabilities will look like. So I guess from my point of view, we could get AI scientists to the point where, with current models, we could automate workshop level submissions, and probably the lower end of conference submissions. But I think we've yet to see the AI scientists propose something, we definitely have not seen the AI scientists propose anything, paradigm shifting or like crazy, kind of, invent the new transformer or kind of, invent the next brand of neural network. Maybe this is just a question of like letting it run for long enough. It's yet to be seen, but I think uh, at this stage, I think researchers don't need to worry too much. And this is more just like a really good muse and a really good way to like brainstorm ideas and get inspiration. And we mainly see this being used in tandem with human researchers to sort of like guide the input. What's going to happen with, I guess, like future um, generations of foundation models is anyone's guess. Like, we were discussing like IMO before. I think at that point we have to think, I guess, like what are the future implications for everyone in the world at that point? Mathematicians, AI researchers, anyone with a job. I think this will really tie like very closely um, in with the rest of the conversation with future generations of models. And yeah, hard to predict for sure.
Yeah, I agree. My naive guess is just around 2030 or something, which is kind of why I'm sort of trying to diversify my career. In
Yeah, I think so. But
Cool.
I'm also like cautiously optimistic about like what happens one level up from this. Um, right now, it's really like it's still going to be 90% human. But what happens when AI comes up with like not necessarily like the paradigm shifting ideas, but what if um, what if it can automate like PhD level research? Although that's a very broad category, like because that could be like also like world changing as well. What if it could like operate at the level of, like the average PhD researcher? Then what could you do with that? Could you, then at that point, maybe like everyone can be a professor at that point, and everyone can have like their own communities of AI researchers like working on their ideas, which I think is a really exciting prospect. Yeah, and I kind of see that as like more what we need to contend with in the next few years, um, rather than us all being put out of jobs. So I'm excited for that.
Do you have any personal plan to sort of like prepare for the when you know researchers are going to be replaced or something?
I hope that won't be anytime soon.
Okay.
I don't know. Maybe I'll make music.
Nice. It's very good to know. Tanis, do you have any comments?
No, nothing else. Yeah, but this was very, very interesting paper. And thank you, Kong, for joining us.
Thank you.
Yeah, thank you so much for having me.
Cool. Aaron, what paper do you want to cover next? Do you want to
I think
cover the?
I covered.
Do you want me to cover next, or?
Yeah, you go ahead.
Okay, in that case, I will cover two papers, which is SAM2 and Segment Anything in Medical Images and Videos. So I will cover those two papers. Give me 1 second to, I guess, pin it to the space first, and then I will talk about it.
By the way, we already have spent an hour, so we can probably make each paper a bit shorter.
Yes. So of course the SAM2 is from Meta, and let me just pull up my notes. Where's my notes? Okay, so for SAM2 is basically, I'm sure many of you have heard of SAM, the original SAM model, which is Segment Anything model from Meta from last year, April of last year, which is this pretty general sort of segmentation foundation model that they trained. Yeah, it was basically, you can label something with a point or a mask or a prompt or whatever, and then or a bounding box, and you could just easily segment with this model, and it was achieving state-of-the-art results. Yeah, so it was very interesting work that they did. And this paper kind of continues off of that, and it's basically an improvement, but also more importantly, it allows you to segment videos as well. So it's not just like an improvement in the performance on the image capabilities, but also adds this whole new capability of video segmentation. So yeah, I'll talk a little bit about the architecture and also how the model was trained. So basically, it basically for videos, for example, of course, you can put you can put prompts in terms of for example, points or bounding boxes or even masks, on individual frames of the video, and then you can for example, try to have it segment over the course of over the course of the video, so you can see how you want to for example, for example, would label maybe the first frame and then try to get the segmentation mask for the remaining of the video, or label it throughout at different points in the video. But then for image input, basically the input, it basically behaves similarly to the SAM1 in terms of how you input your prompt or your mask or whatever, and get how you get the output segmentation mask. And so then for videos, you have an image encoder, and so that image encoder is run on each frame in the video. The image encoder is I guess it's called a Hira model. I guess this is a hierarchical transformer architecture, also developed by Meta. It was developed by Meta last year, and this Hira encoder is pre-trained with a mask autoencoder task. So it's a MAE pre-trained Hira. And so that's the image encoder that they use. So that's different from SAM1. And so this sort of Hira encoder is hierarchical and provides sort of multi-scale features for the model to use. Okay, so that's the image encoder part. Then the other aspect is that those image encoder features are passed into the sort of attention or transformer part of the model. But the whole idea here is that because you have video, you want to basically condition past frame features. So, you have the transformer blocks. You have a bunch of transformer blocks that are stacked. The first one takes in the input image encoding of the current frame, coming from your image encoder, your higher model, and then each transformer block is performing self-attention followed by cross-attention, and the cross-attention is then it's cross-attending to what is called memories of previous frames. So we'll talk about how these memories are generated, and basically these memories are stored in a memory bank. And so I'll talk a little bit more about that later. But basically, the idea is that in your transformer part of the model, you have this cross-attention that is allowing the model to look at previous frames, and that influences the generated segmentation. Okay, so basically you have the model has the image encoder features going into this memory attention. This memory attention then gets passed into this mask decoder, which takes so the mask decoder takes an input from the memory attention and also takes an input from the prompt encoder. So this is kind of similar to the original SAM paper as well, where they also have this prompt encoder and this mask decoder. So basically, you have to be able to encode the prompt in some way for the model to understand. So they have this sort of positional embeddings that represent, for example, the points or the boxes, if that's how you're labeling your data, that's how you're labeling your image. So you have positional encodings. You could, if you have like text that you're trying to encode, they have like a clip text encoder. And then like if you're doing dense prompts, like a mask, like for example, if you're labeling the first frame of the video and you want to then segment out the rest of the video, you have the first frame has you would have to label a segmentation mask, and that would be embedded using convolutions, and that's summed with the image embedding that you get for that particular frame. So they have these embeddings that are then associated with the prompt that you gave the model, and that's passed into this decoder, which is also a bunch of transformer blocks. And so this is taking in so basically you have you have like cross attention between the prompt embeddings and the frame embeddings, the embeddings from the image frames that we got from our memory attention. So basically you have the frame embeddings that you come from your image encoder. They're processed by the memory attention part, then they are passed into the decoder, where there's cross attention between those frame embeddings and the prompt embeddings. And then so then that basically gives you a sort of segmentation mask for that image. Basically, that you have like an MLP that is producing an output token for each pixel basically, or each location in the image, and so that is produced by that mask decoder, and then so there you get your mask for that specific frame. But now the question is like, okay, you have the frame that you're getting the mask for, but now you want that to be part of your memory for the next frames. And so that's where the memory part of it comes. So you have a memory encoder and you have a memory bank. So the memory encoder basically just takes the output mask and downsamples it with a convolutional module, and then sums it element-wise with the frame embedding from the image encoder. And so that you have this sort of, that's where you get your memory, and this goes into your memory bank, which basically stores like the n recent frames. And then that is then, those frames are then, those frame embeddings, the memory embeddings for those frames are then passed into the memory attention so that you can do the cross attention to the previous frames. So yeah, that was all very complicated. But hopefully you have some sense of like the general idea is like you have these embeddings for the images, and they are being processed by transformer blocks and cross-attending with the prompts that you have, and that produces a mask. And also then you have this memory component, which is I think the main component that's different from the previous SAM model, because the memory component allows it to deal with videos. So those are that's kind of the summary of how the model works. And of course, the nice thing about this paper is like it also, they do this sort of very data-driven approach to or data-centric approach to training this model. So actually the model is trained jointly on image data and video data. So for example, for the images, they use the same data set that they use for the original SAM model. It's called SA1B. So they have like 1 billion images for that. But then for the videos, they have this sort of data engine where you have like, for example, initially you have to you have the human annotations. They're annotating per frame. Of course, it takes a long time. They're using the SAM1 model to help them label per frame each image, because the SAM model works for images. So they're using that to help them annotate per image in the video. But that's still going to take a long time, and so they only do this for like 1,000 videos, and they collect. So that's a pretty small data set that they have there. But then they basically train a small sort of SAM2 model that only accepts masks as prompts. So basically so that's like, this is their first version of their SAM2 model, and that's trained on their data set, where basically, okay, it's, you have the mask from your first image, and then you have to utilize this SAM2 mask model, as they call it, to propagate the annotated mask from the first frame to the other frames. And so that they get some rough data for the full video, for example. And then they start then training their full SAM2 model, which accepts a variety of prompts. And then they train the model on data, and then they edit, and then they apply the model to data and edit, of course, the predicted masks if there's any issues. And so they actually say that they retrained and updated SAM2 using collected annotations 5 times. So they keep doing this sort of data labeling, utilizing the current version of the model to label the data, adjusting it. They continue like that. So yeah, they have this whole data engine pipeline that's very sophisticated and allows them to collect data, a lot of data. So they have their data set that they have is, which they release under a permissive license, by the way, so people can access it and use it. Their data set has 50,000 videos with 642,000 masklets. They call them masklet, which is basically the sort of spatio-temporal mask. And so, yeah, they have that huge data set. They also have an internally available licensed data that they further use to augment their training set, which comprises of 62,000 videos and 69.6 thousand masklets. So actually, it looks like their internal data has more videos, but maybe is more sparsely labeled and not very densely labeled. So that's an interesting thing to also note. In terms of results, they talk about like, yeah, their model is generating better segmentation accuracy with 3 times fewer interactions. So basically saying like, okay, if you are going to try to label a video, you have like this interactive segmentation where maybe, okay, you label the first frame, you see how it is labeling the rest of the frames in the video. Maybe you adjust some of the frames here and there while you look, while it's segmenting out the image, the video. But what they're saying is that like you, compared to maybe some of the other methods, you only need to kind of relabel maybe around 3 times less compared to maybe some of the other methods, for example. And then, of course, the other sort of like test scenario is basically just only prompting the first frame and not actually prompting any of the middle frames or any of the rest of the video. So if you only prompt the first frame, yeah, basically it outperforms baselines on 17 of the data sets. And again, yeah, it's outperforming all the previous methods. So that's for video, but then also for just plain image segmentation, the model achieves better performance. So it achieves higher accuracy than the original SAM1 model without using any extra data, and it's also 6 times faster to run. And they note that this can be mainly attributed to the smaller but more effective Hira image encoder in SAM2. So it's because of this hierarchical multi-scale image encoder that they are also able to just achieve better performance overall on image segmentation. So yeah, that's SAM2. Before I move on to SAM2 for medicine, does anyone have any questions or comments? I know that's probably a lot to take in.
So obviously there are some like a very important practical implications of SAM2 to like robotics and VR. Do you have anything in your mind? Like how does this this is video, and I don't think there's a lot of video data in medicine. How does it how is it useful?
Yeah, I mean, I get to the SAM. There's a separate paper about SAM2 for medicine, so we'll get to that, and I can talk about how it's used in medicine. Yeah, I guess I'm not as familiar about like, I mean, robotics, I guess, is more like, yeah, you can like segment out the I guess, yeah, when you have these videos of like the robot performing its actions, you want to segment out the objects. I guess that's the main use case there. But yeah, I guess I don't know if I don't know exactly what you're asking. If you're asking about like the applications of SAM2 to medicine, I'll talk about that next.
Like beside medicine, so the paper says like important applications in AR, VR, robotics, autonomous vehicles, and video editing.
Mm-hmm.
Do you think of anything else? Like
any other applications? I don't know. That's a good question. I mean, you basically have all the same applications for image editing, of course, and image segmentation and all of that. And I think video editing, that's a good point. That's going to be a very interesting application, just to be able to like, edit out maybe objects from a video or things like this. What other applications? Yeah, I don't know. Nothing immediately comes to mind as to other potential applications.
Anyway, it's fun to think of applications. Could be useful for some startup ideas.
Mm-hmm. Yeah. Yeah, I'm sure there's probably lots of interesting startup ideas that you could come up with for this. If I recall correctly, I think I saw a tweet somewhere. I think it was like Yassine who said that like Dingboard was like heavily powered by the original SAM model, and was very much inspired by when that model was released and things like this. So you could imagine that like, yeah, in the future, SAM2 could also be used to power some interesting products and startups. Yeah.
Yeah, so instead of using Dingbot for creating memes, you can use SAM2 for creating video memes.
Yes, exactly. I think that would be a very fun application there. Yeah, I mean, just generally, yeah, I think like SAM2 will be very useful for video editing in general. Yeah. Cool. If there are no questions about no other questions about SAM2 and how it works, because yeah, it's a bit overwhelming in terms of how it works. There's a nice if you go to the SAM2 paper, of course, there's plenty of figures that kind of better explain the flow of everything. So figure 3, for example, shows the overall architecture. And then like there's a very detailed appendix as well that goes over the architecture. So for example, figure 9 talks about the mass decoder architecture. Figure 11 talks about the annotations and how that works. So yeah, if there's a lot of lot of detail in the paper. So if this is interesting to you guys, you should definitely check it out. And I think it's just also a good paper talking about the sort of data engine stuff as well. I think that's also a very interesting kind of almost like a nice case study on how to do that really well. So yeah.
Sorry, this is not really related to your paper per se, but I've seen a few people commenting that they would really appreciate if we could share visual information. Unfortunately, X-Space currently does not support visual information sharing, but another option is video streaming on X, which we discussed that before privately, that that sort of lacks the interactivity of space. But I think the interactive advantage is not that much, I guess. What do you think?
Yeah, I think we have to explore this further, and I think I guess personally, I think maybe I'm hoping we'll see how it goes, but like X will like improve some of these aspects on spaces and live streams. And I think some of these ideas in terms of like doing screen sharing and video stuff on spaces is kind of on their radar, and like they're planning to potentially add that soon. So I'm also hoping that these sorts of things get added soon enough. But we will have to evaluate. Yeah, we can reevaluate if we want to use maybe live streams and things like this at one point.
Yeah, we could try live streaming in the next session if that's okay.
Yeah, we can think about it. Yeah. Yeah, someone was suggesting video X based and live stream, which streams to X, and we tried doing that actually. Yeah, David is saying this. We tried doing that, and that didn't work for some reason. I forget, we had some technical difficulties getting that to work. So, yeah, we'll have to see what the best way of doing this is. Okay. Next paper that I want to talk about. I was talking about SAM 2, and of course, coming from a medical AI background, so I'm obviously very interested in how these models are used in medicine. There was a recent paper that evaluated if SAM2 is better for medical image and video segmentation. So basically, people have already explored using the SAM model for medical segmentation, segmenting, for example, X-rays and CT scans and MRIs and mammographies, microscopy images, ultrasound, and people have been applying SAM to these out of the box, or also fine tuning SAM for medical for these medical tasks. So, for example, they have a MedSAM model, which was fine tuned on a whole bunch of medical tasks, for example. And so now this paper that I'm talking about here, which I've pinned to the space, is evaluating if SAM2 out of the box is better than SAM1 and also better than this fine-tuned MedSAM model. So they are benchmarking over 11 different modalities. I mentioned some of them already, like CT, MRI, PET, ultrasound, mammography, light microscope, OCT. There's several others as well. And then the way that they are prompting the model to do the segmentation is with a bounding box. So they found out that in the past that doing this bounding box prompting is more efficient and has fewer ambiguities and leads to better performance than doing like a point prompt. So with the SAM models, you can prompt it in different ways. You can like put a point over the object that you want, or you can like put a bounding box over the specific object. So there's different ways of prompting it. So they're saying, at least in this medical domain, the bounding box prompt is typically better. So that's what they use. And so then basically what they've observed is that SAM2 is better than SAM1 on many different domains like MRI, light microscopy. It has lower scores in some other domains like PET and OCT, And then in many domains, it also has this comparable performance, like CT, X-ray, ultrasound, mammography, etc. They have comparable performance to SAM1. This is, of course, like the out-of-the-box models. But the other thing to note is that the fine-tuned SAM1 model, which is this med-SAM model. So this is SAM1 that was fine-tuned on a whole bunch of medical tests. That model consistently outperforms both SAM1 and SAM2 on most of the modalities. So it seems like, even if you have a better segmentation model, like out of the box general segmentation model, the fine-tuned model that was fine-tuned on the medical test is performing much better, even though it was fine-tuned with an older model. So that was looking at just images. The other thing is that, of course, SAM2 has the ability to process videos. And the nice thing is then, okay, you can formulate 3D images as videos. You could say, for example, like with the CT scan, basically then the CT slices are frames in a video, and you can process it that way. And so actually, by doing that on CT and MRI images, SAM2 does perform better. But for PET images, it's performing poorly, and it's actually easier. Like, you get better performance if you just do like SAM1 on each individual slice by itself. Actually, it's interesting. These PET images, like overall, it looks like the SAM2 seems to struggle with these PET images, even with like if you just look at a 2D versus and also the 3D one. So that's another thing. Maybe that's a domain that's, again, maybe not as much data and needs to be trained separately for PET images. Something to consider. Okay, and then the other thing is like, okay, so they said if if the model is the MedSam model, which is a fine-tuned model, is performing better, then yeah, maybe this sort of fine-tuning is important to do. So they only did a very preliminary experiment where they fine-tuned one of the smaller variants of SAM2 on a very specific 3D abdominal organ segmentation data set. And of course, they observed that the model does perform better if it's fine-tuned. But again, that's a very small sort of like preliminary example, and I think future work would probably have to do a more comprehensive fine-tuning on different domains and larger data sets and larger model and things like this. But yeah, I think it's a very interesting paper. Basically, the conclusion is that SAM2 isn't always better and then SAM1. In many cases it is. You just kind of have to evaluate it on a per case basis or per dataset basis. And then on top of that, the fine tuning on the medical domain is very useful. And like even the old SAM model, because you had the version that was fine tuned on the medical domain, the med SAM model, that's outperforming everything. So, fine tuning, even though like you have these general models, it's very useful to still fine tune on domains that, like the medical domain, where it's very different from general images, right? Like, they look very different from natural images. So fine tuning often seems to help for medical domain. Yeah, so that's that paper. Are there any questions about it?
Yeah, thanks for addressing some of my questions earlier.
Yeah. Cool. If there are no questions about that, I guess we'll move on to, Aaron, you were going to cover the Llama paper, Llama 3.
You know what? I can cover the Agent Q paper, which is actually probably more new to many of you guys. It was like
okay, fair enough.
Yesterday,
okay,
or 2 days ago, I think. Actually, this one's so basically they released a web state-of-the-art web agent. Let me see. So okay, Multi-On, a startup, they present Agent Q, the state-of-the-art autonomous web agent that can plan and self-heal. So self-heal means that sometimes the agent goes to bad trajectories, then they can recognize that it is on the wrong direction, so they can move back to the correct path. So so the current existing problem is that current methods such as supervised fine-tuning on curated expert demonstrations often fall short on agentic multi-step tasks due to compounding errors and limited exploration data. This is also the case for even embodied agent. So these approaches yield suboptimal policies, particularly in dynamic environments demanding complex decision making and adaptive learning. So the solution they proposed is basically Agent Q combines guided MCTS and AI self-critique with iterative fine-tuning and leveraging DPO. So this method enables LLM agents to learn from both successful and unsuccessful trajectories, which enhances the generalization capabilities in multi-step reasoning tasks. So they proposed three main components: guided search with MCTS, AI self-critique, and DPO. So MCTS part basically autonomously generates data by exploring different actions and web pages. They balances exploration and exploitation. So MCTS expands the action space using high sampling temperatures and diverse prompting, ensuring diverse and optimal trajectory collections. So for self-critique, at each step, AI-based self-critique provides variable feedback, refining the agent's decision-making process. So this step-level feedback is crucial for long horizon tasks, where sparse signals often lead to learning difficulties. So this is very similar to what Charlie was saying at the beginning. So yeah, basically, looks like everyone's going to the same direction. So sounds like that's the right direction. And also DPO. DPO fine-tunes the model by constructing preference pairs from MCTS generated data. So this off-policy training method allows the model to learn effectively from aggregate datasets, including the suboptimal branches explored during search, improving success rates in complex environments. So the results are very impressive. In real-world booking experiments on open table benchmark, multi-ons agents drastically improved the zero-shot performance of the Llama 3 model from 18.6% success rate to 81.7%, which is a significant jump and far better than GPT-4o or any like a model, any open model presented based on GPT-4o. So yeah, actually, just one day of autonomous data collection, they further improved to 95% with online search. These results highlight their method's efficiency and ability for autonomous web agent improvement. So yeah, okay, let me give you more details. So first, architecture. They used what is called Agent Ohana XLAM model by Salesforce, which was released like 4 months ago. So actually, this is a fine-tune of the pre-trained mixture instruct on a mix of agentic applications, including WebShop SFT data. So as for the results on WebShop benchmark success rate, XLAM model performs worse than GPT-4 by 10 points. So XLAM is our baseline here. But after DPO is applied, it already outperforms GPT-4 slightly. And applying beam search on top of DPO doesn't result in any meaningful improvement. But applying MCTS to XLAM outperforms DPO by 8 points, which shows how crucial MCTS is. And I think DPO gets another 2% improvement, which ties with average human performance of 50% success rate. And human experts achieve 60%, which is still ahead of their model. Yes, it looks like this benchmark is quite a bit hard, even for human experts. On other benchmarks like OpenTable, the benefit of DPO on top of MCTS is more significant, which led to the success rate of 95%. So I have a few questions. I believe the same approach works for various other agentic settings, including embodied agents, whether in virtual space or real world. MCTS in the physical world is not straightforward and less studied. So this should take more time. Does anyone have any insights on this? Tanish, have you heard about it?
Sorry, what was the question? Sorry, I just missed that for a moment. What were you saying?
Okay. Like MCTS for like physical world, like a robotic.
Oh, I'm not sure. Yeah, I feel like I heard something like this, but I don't remember now off the top of my head. But yeah, that's a good question.
Yeah. Anyway, yeah, I haven't seen many papers.
I think it's like, yeah, like the sort of like path planning stuff, for example. Like I think it's like probably used more like in a sort of like traditional RL sense, MCTS.
Yeah.
Maybe not so much. I think maybe it hasn't as much been explored in the sense of like, you know, utilizing these robotic foundation models and then applying MCTS to that. Which maybe there's some sort of opportunity there to do some interesting research. But I think, yeah, like MCTS, like I may have seen it like more like some like path planning or like more like standard sort of RL for robotics kind of things.
Yeah, agreed. So this model is not open sourced and probably will not be by this startup. But I believe open sourcing this model by a third party will attract huge attention. So yeah, I wonder who is going to do it. Like, yeah, this is going to be very, very interesting. Maybe Electro AI can do it. Maybe they don't have that much resource, but yeah, that'll be. What do you think? Oh, never mind. This is not.
Yeah, I mean, I think it would be interesting if someone had an open source version of this. And I'm sure someone will make one soon enough.
I will just probably keep reaching out to people and if they're interested or not.
Yeah. Cool. So does anyone have any questions about this paper? Doesn't seem like it. Aaron, was there anything else you wanted to add about this paper?
Not much, actually. This I'm still reading this paper. It's such a new paper, so I still haven't.
Yeah.
Yeah,
I think this was just released just yesterday, so it's pretty brand new.
Yeah. Actually, this paper is actually probably like most interesting paper, like a most important paper. It's kind of hard to say, but obviously the first two talks, like Charlie and Kong's these papers are obviously interesting, but this one's, you know, kind of like very impactful in a different direction. So I think more people should talk about it.
Yeah. Okay. I guess I'll just quickly cover this last paper, the CogVideoX. I guess we'll probably just skip the llama paper for now. Maybe because it's probably a lot and we don't have much time. Like we're already like pretty longer than usual. Maybe we can cover it next week. Maybe we can talk about it next week if we have time.
Have a CogVideo right?
Yes, I'll quickly cover that right now. So let me just let me pin it to our space and pull up my notes. So yeah, I mean, I like this paper. CogVideoX is actually a pretty good paper. And it's basically, yeah, they have they're training a text to video model. And so, yeah, I mean, we haven't seen a whole lot of these sorts of text to video models open sourced, and at least the ones that have been open sourced aren't particularly that good, I guess I would say. And there's still a lot of work to do in the space, mainly, especially in the open source area. And of course, the reason a lot of it is because it does require a lot of compute to do this sort of work. But videos, hold other dimension of compute, I guess. So much more compute you need. But anyway, this is a paper from, I guess, the sort of THUDM group. Like this is like the group, they have like a lot of these sorts of like Cog series of models. Like they have CogVLM, which is like one of the best image capturing models. Like they do a lot of like interesting sort of they have like the chat GLM models. CogView was their image text image model. So yeah, they have some really interesting work that they've been doing. So now they're working in the video space. They had, I think, previously trained one of these CogVideo models in the past, but this is a new one that they're doing, CogVideoX. And so the approach here is, again, a pretty standard approach that I think basically both in text to image and in text to video, you kind of converged on this approach, which is basically latent diffusion with a sort of diffusion transformer. But in the case of video, the way that they have this is they have to train a separate autoencoder, a VAE, to compress the video into latent space. And typically one of the approaches has been compressing each frame of the video, and so you just use like an image autoencoder and compress each frame. And then you also have your model architectures like trying to process this in like a temporal manner. And so that like all kind of is like very specific to the video domain, and kind of maybe it's can get a little bit complicated. This approach here that they're doing is basically the VAE is compressing in a sort of spatial temporal manner. So like you just have the whole video and it's being compressed all together. It's what I say, it's a 3D VAE, because it's like you've got the 2D image dimensions and then also the extra time dimension. So it's like a 3D VAE. And basically the encoder and decoder is basically comprised of a bunch of ResNet blocks that are stacked together. They have a 4x compression in the temporal dimension and 8x compression in the spatial dimension. And then the important thing is that like they want to make sure that it's temporal, like there's no like future information that is influencing the past or present predictions. So they have this sort of temporally causal convolution, which has all the padding at the beginning of the convolution. So they have this sort of temporally causal convolution to make sure that you're able to keep the sort of causality in the temporal dimension and in the sort of video, with the video. Then they also notice like, okay, we can train we can train the VAE on lower resolutions and fewer frames at first to save computation. They notice like, actually, the encoding like encoding into a higher spatial resolution seems to work very well, pretty well if you train it on the lower resolution. But actually, if you want to do longer videos, that's a little bit harder to do if you trained it on fewer frames. So they have to then fine tune that model that they have on longer videos as well. So that's how they do their VAE. And then they have the latents that are then passed into the transformer. And so the transformer, of course, has to be able to handle these sorts of 3D latents. And so, for example, like it's a pretty standard transformer architecture, but it has things like a 3D rope embedding. So it's like a rope embedding that is able to handle these sorts of 3D latents. And then the other aspect is like it actually does something kind of similar to, I would say, like Stable Diffusion 3 with the MMDIT architecture, where basically the text and the video are kind of processed separately. And then there are these sorts of full attention layers that process everything together. But the rest of for example, the layer norm blocks of the transformer process the text separately and the vision separately. But then you have like the full attention, which again is a 3D full attention. So you got to again do this across the both dimensions, the spatial dimensions and then temporal dimensions. So you have this 3D full attention, and of course they're able to leverage the recent advances in speeding up attention computation, using things like flash attention and stuff like this to make it computationally feasible. And so that is the architecture. Again, there's lots of interesting aspects of how they train the model and the data pipeline and things like this. So for example, they use both images and videos for trading, basically treating images as a single frame video. They use progressive trading from a resolution perspective. On the diffusion side, they use standard things like feed prediction, zero SNR. They use the same noise schedule as latent diffusion. Pretty standard things here. Then the other thing is like, you'll have videos of different lengths. So in order to ensure you have consistent shapes, you have to like pack them together. So just like when you have like with trading like language models, you pack your batches with text to like meet a certain context length. You pack them all together. So similarly, they do the same thing with the videos. You pack the videos together into a single batch. And then they have a total of about 35 million clips that they train on. And each clip averages about 6 seconds long. They basically have to do a lot of filtering to get this. So, for example, they want to like make sure that the videos have a lot of dynamic information and not like, for example, videos of something that's just still and not moving or things like this. So they actually like label 20,000 data samples with a bunch of like tags about like if it's like negative tags about the videos, and then they actually train a model to predict those tags and filter out based on that. And then they also have this the captioning. So they actually do a synthetic captioning of the videos, because the original captions are very short and concise captions that don't provide much information about the video. So of course they do this very they have a synthetic data pipeline there, where basically they take the video and then they separate them out into frames, and then they use a image caption modeling, and like in this case they're using the CogVLM model to basically caption each frame in the video, and then they actually summarize all those image captions into a single video caption using a language model. So they, for example, utilize GPT-4, but to do this over thousands or millions of videos, that's like a little bit difficult. So they actually distill the GPT-4 into the GPT-4 predictions of the video captions from the image captions. They distill that into a Llama 2 model. So they fine tune a Llama 2 model to be able to do that, and then they can extend run the Llama 2 model to be able to predict the video caption, the long video caption from the collection of image captions for each of the frames. So that's how they basically put together their video captions for their data. And yeah, that's how the model is put together. They evaluate their model on some sort of video benchmark and show that it's achieving better performance than like even models like Gen 2 from Runway, Pika, Video Crafter, OpenSora, etc. They also did a human evaluation with 100 evaluators, comparing it to the Kling model, and they were seeing like, according to things like instruction following, physics simulation, all these different sort of qualities, that their model is better than the generations from the Kling model. So yeah, that's the CogVideoX paper. They've only open source right now the 2B model. I would say to take a look at the videos yourself, like to kind of judge. I think like they talk a lot about like, oh yeah, like these are better on the benchmarks, but I think like it's still like I think it's not like significantly better, and I think it's still like on par with some of the other existing sort of models out there. So I don't know like if we can really say it's significantly better, and I think maybe more comprehensive evaluation needs to be done, and a qualitative evaluation to actually fully judge that. And also they've only released the 2 billion parameter model. They also do have a 5 billion parameter model that they've trained, but they haven't released that yet. And they said that they're going to train larger models as well. But I think it's a good paper kind of describing how these sorts of models are trained, and it's great that they are at least releasing the 2 billion parameter model and the corresponding code with that. So yeah, I think it's quite interesting. Are there any questions about it?
I don't have any question, but yeah, it's great to have another open source video models. Like I'm sure Black Forest Lab is gonna eventually put up some very nice video open sourced.
Right.
Yeah, but
Right.
it's
And I suspect that the Black Forest model will also we'll see, but I think a lot of you'll probably see a lot of similar sort of architecture and setup in terms of you have a 3D VAE and you also have sort of some sort of like this expert transformer architecture that looks a lot like an MMDID architecture. So I think you would it's probably going to be a very similar sort of architecture is my hypothesis, my guess.
Yeah. So given that image and video generation, like open sourcing it is a risk for big tech, like Meta. So Meta is not gonna do llama moment for video, but probably.
Yeah.
But
Yeah, probably not.
So we have to rely on Black Forest Lab, maybe some other open source lab in the West, and Chinese models, I guess. And because China, they don't have to give a shit about YouTube. They can just keep using it.
Yeah. Yep. Okay. If there are no questions, I think someone was, someone was asking just about like if, distilling the video caption from GPT-4, if this synthetic data improvement might work in other areas that like good label sample. I mean, yeah, I think there's a lot of interesting work about synthetic data improvement. Actually, I think Aaron had covered some of the recent advances in there in one of our earlier spaces, if I recall correctly, in terms of like synthetic data and distillation and stuff like this. Yeah, Aaron, I think you covered this a while back, right?
It's not about video, right? Which one was it?
Well, not about video, just generally in like synthetic data, I guess for language models and things like this.
Oh yeah. Actually, I think I've covered multiple of them, so I don't know which one.
Yeah.
It is, but yeah.
Anyway, so yeah, I guess someone was asking about that. So yeah, you could like take a look at maybe some of our previous recordings that we have for more discussion about that topic. Cool. Someone is asking how much compute would it cost to how much would it cost to replicate in terms of compute? That is a good question. I'm not sure if they actually say how much compute was used. I cannot immediately find it. I'll reply if I do find like a compute cost in the paper. But when I was reading it, I don't remember seeing anything like this mentioned. But that is a good question. I'll reply if there's anything, if I find it in the paper.
The video length they used is like 6 seconds, which is quite a bit short. So obviously,
it is.
Unless your model is as good as Sora, you probably will notice like and like a video not being coherent over 6 seconds anyway. So you probably don't have to try anything beyond 6 seconds. But yeah.
Yeah, let's see. I'm just trying to still looking here. 6 seconds. Yeah, I don't know. I can't find anything about how long they used to train it. Anyway, maybe if I do find it, I will reply. Okay. If there are no other questions, I think we will end. Aaron, did you want to add any other comments? Any other things you want to note?
Yeah, I think we already I already mentioned everything I wanted to share. So yeah, that's all, I guess.
Okay. Cool. Well, thank you everyone for joining us. I know this one was a little bit of a longer space, but I think we had some really good discussion from the authors of these different papers. So that was really fun.
Yeah.
And yeah, I guess we this is our first one after a few weeks. So I'm glad that a lot of people are still joining and interested, and hopefully you all found this useful. And as I've done in the past, I will post the recording for this in the next so the recording's already available on Twitter, but then usually I also put it as a podcast now. So we'll post that in the next couple of days. And then we'll see you all next week.
See you.
Bye, everyone.